So last week I recorded my classes, but because of some settings issue with the recording software, it was not properly recorded. So I am planning to redo the session again. Not with everyone. I will record it personally and I will upload. I will try to cover all those things which I discussed in last week there, and I will upload. I'm sharing my screen. Once it is visible, please tell me if it is visible or not. Is my screen visible now? Okay, thank you, Vaishak. Yeah. So, yeah. So, in our previous session, this is the discussion nutshell. Our microcontroller PIC16F877A has 5 port A, port B, um, port C, port D. So every port has their own registers for accessing the port value and managing the port value. Also uh, changing the behavior of the port, like whether it is input and or output. So for port A, it is tris A and port A. Port B, it is tris B and port B. Here I have to make B. Please read it as B. Okay. For port B, it is tris B and port B. RC0 for port 0, it's tris C and port C. Port D, it is tris D and port D. And for port E, it is tris E and port E. We have three 8-bit port, that is port B, port C and port D, and 6-bit port A port and 3-bit port E port. So what will happen if you are writing one, as we discussed, writing one to a particular register inside the tris will make the corresponding pin input. Writing 0 to the corresponding register of a particular pin will make that particular pin output. If you are writing the port register 1, it will make that particular pin high, which means 5 volt in the case of 16F877A, 0, which will make that particular pin low. Okay, so today we are going to discuss about this thing, like automatic temperature controller. We learned last week, we learned control structures like loops and conditional statements. So we are going to apply that knowledge here. So during that discussion, we will discuss few things about those things, like these are the discussion which we had last week. So conditional statement, if else, else if, nested if, switch, break and continue statement in C, few operators in C, and loops in C. So we are going to apply that knowledge today. So today we are going to start doing a project called automatic temperature controller. So we will be taking help of GPIO, general purpose input output pin of ADC, microcontroller. Also, we are going to use the ADC peripheral of the microcontroller. So two peripherals will be deeply covered. Okay. Also, we will try to learn those things, try to implement those things which we learned in our previous session, like control structures and all those things in this stage. Okay, going to the next slide. Okay, so we are going to do a project. Okay, so suppose think in a way that you are working in a company and your company got a project called automatic temperature controller. So what will happen once your company gets a project? So your company will have hardware engineers, software engineers. So They will discuss with the client. Top level discussion would be there. They will come into a conclusion that they need this kind of requirement, like temperature need to be measured, and these kind many devices to be controlled, and the devices available are working based on AC. Few devices are working based on DC, and they need some visual indicators, audio indicators. These many inputs will be coming from the customer, and these high level requirement engineers will collect all this information, and they will make a complete picture based on that discussion. So the picture would be like this. They will create a block diagram, top level block diagram for that particular project. So they will came in. They will come into a conclusion that they need a microcontroller for that particular project, and they need a temperature sensor, some visual indicator, audio indicator. They need to control an AC fan. Also, they need a few switches like auto manual on off switches. So these many things will be happening in the discussion, and they are making a picture out of that discussion. So during after the discussion, this is the thing which is going to happen. Hardware software co-design will happen. First, it is requirement and specification. They will get it from the customer or the party um, which they want this product. So there would be a top level architecture, how it is it should be constructed, the way in 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 all the way, like how the end product should look like. All the architecture level discussion would be happening. Then they will separate the design into hardware design, then software design. These things will happen parallelly. So during the hardware design and software design, hardware engineers and software engineers will be continuously interacting. Software engineers will be testing that software with the help of simulation software, like Proteus or some other softwares are also available. Hardware design engineers will also do some simulation and all, before designing the hardware. So they will also do some simulation and testing inside inside the some softwares available like OrCAD. Some other softwares are there for simulating the hardware. Uh, they will do their own simulation also, and then they will start implementing. Once the hardware prototype is ready, they will integrate the software with the hardware. Then they will test mm, the board which they designed. So after the testing, they will give the product to the customer for review. If there is some feedback, then there would be a requirement and specification change would be there. Again, some architecture plan would be there. Again, hardware design and software design would be there. This keep on repeating. Like there is one particular method we follow in our software development and in our company, that is called agile method. In that agile method, this kind of uh, things would happen repeatedly once the product became a complete mixture. So yeah, let's go back to the block diagram. So we have this block diagram. Based on that block diagram, hardware engineers would be selecting few things like which temperature sensor they are going to choose. So which microcontroller they want to select. So there are so many things which they will consider, like the availability of the chip, how many quantity they can provide, till which year they will be available to support. So too many things they will think. Okay, so let's go to our discussion. We are focusing on the software development. So you can always read such a things in Google. You can search in Google like hardware software co-design. You can read it how it is working. So it is good to know uh, one- if you want to be in the electronic product design area. Okay, So let's see the sensor which we are going to use here. So right now I choose a select temperature sensor called LM35. Mm, this is that sensor. You can see it looks like a transistor. The operating voltage, the VCC you can provide is between 4 volt to 30 volt, 32 volt, and the output which you are going to get is analog output, which is 10 millivolt per centigrade, which means if you are getting 1 degree Celsius, you will be receiving 10 millivolt. For 2 degree Celsius, it would be 20 millivolt. 3 degree, it would be 30 millivolt. Okay, this is how the temperature sensor responds. Also, there are many temperature sensor available in the market. Based on the customer requirement, hardware engineer would choose the component. Okay. Also, so what software engineers need to know about this? Software engineer need this parameter. How much increment will be happening for 1 degree Celsius? This kind of information is software engineer needed. So software engineer is going to monitor this temperature, right? So he need to know how the temperature, how the voltage, how the analog voltage output is varying based on the temperature. Then only he can um, correctly implement an algorithm for the temperature reading software. So let's go back to block diagram. So based on the block diagram, hardware engineer will discuss with the software engineer. Then finally they will plan a schematic. Okay, so they will discuss few things and they will plan a schematic. This is the schematic which we are going to use for this particular project, automatic temperature controller. As I said, we have a visual indicator LED here which is connected to RB0, and a buzzer which is connected to RC0, and a temperature sensor connected to RD0. So I need to explain one thing. So this is a temperature sensor of type analog. Okay, so this is an analog temperature sensor. So the output should connect to analog port. You can see this port A, RS0. AN means analog. Okay, so it should connect to RS0. So right now I want to discuss in a way that first we will try to learn all the control structures part with the help of GPIO alone. After that, we will learn about ADC. So ADC, if I am starting with the ADC, it would be a bit confusing. Once you have the working software without analog feature, it would be easy for you to create the software. So once the software is ready and we have all the features available and we learned all the basics, how to use the control structures and loops and all those things, then we will go to ADC interfacing. Okay, so ADC interfacing, you need to manipulate few registers, manipulate or manage a few registers inside the microcontroller. So there are few registers, ADCON 0, ADCON 1, and its result calculation. So you need to learn few things regarding the ADC peripheral of the microcontroller. So I am keeping it aside so that we can learn it later once we have a better base in software development. So yesterday I pinged in WhatsApp called bare metal software development. What is bare metal means? We are not using any operating system support. We are not using any operating system support. Like I can explain that your computer is working with the help of an operating system, right? Windows, Linux, like that. So here in our microcontroller, there is no such operating system available. We are writing our own software here. So that is called bare metal. Also, there are microcontroller which is capable of handling operating system, which means you can install an operating system inside the microcontroller, and on top of that operating system you can write your own application. That is a different kind of software development. That is not bare metal development. Bare metal software development is Solely pure hardware related software development. There is no operating system support. You are going to create an operating system for the proper functionality of your product. Okay. You have something to ask now? So you can turn on your mic and ask. Okay. Okay, let's go back to software development now. So before that software development, we need to know the working of the devices in the software. I already told that the software developer and the hardware developer will be discussing and concluding the hardware. Okay, so software developer should know how the hardware is working, not the entire thing, but how the signals should be given, and how the response is coming from different sensors and output devices. So you already know the working of LED, right? So LED is biased with a positive 5 volt here, and it is connected via resistance to RB0, making this particular pin low would illuminate the LED, making the pin high will turn off the LED. So here you can see one buzzer. Buzzer is nothing but a output device which can generate sound, beep sound. Okay. So the customer need a beep sound when a particular device or a temperature becomes high or temperature becomes low. So they need one buzzer kind of thing here, like for generating audio indication. So if you go to the properties, you can see the operating voltage is 12 volt and load resistance is 24, and the frequency is 500 hertz. You can modify and test it once uh, you already have the software installed in your PC. You can play with it. Okay. So how it is working? The buzzer is working. Buzzer is biased with I'm biasing with the 5 volt here. So the bias voltage is 5 volt. If you want to turn on this buzzer, you need to make RC0 pin low. If you want to turn off, you have to make RC0 pin high. Also, I am using the analog temperature sensor in a way that in a digital way. You already know that 10 millivolt will give you, sorry, 1 degree for 1 degree Celsius, you are going to get 10 millivolt, right? Here you can see for 1 degree Celsius, it is 10 millivolt. So I am thinking in a way that I am opening my calculator. So 5 volt is 5000 millivolt, right? Okay, 5000 millivolt. Uh, to get a digital value high, you need to at least 3 volt. So 3 volt means 3000 millivolt divided by 10 millivolt equal to 300. Okay, okay. At least 300 millivolt you have to get in order to have a 3 volt output. I mean, okay, just we will measure. Let's see how much voltage it is coming for 3 volt. I am connecting a voltmeter, DC voltmeter here. So 27 degree, you can see 0.27 volt, which is 2200 millivolt. I need at least 3 volt here, then only I can connect it. I won't get it. I will get only 1.5. Okay, not a problem. We will implement in a different way. So what I am trying to do here is, you can see, you saw it right. For 1 millivolt, I am getting 1.5 volt only. So 1.5 volt, our microcontroller, when if you are reading it in a digital way, it will consider that 1.5 volt as low. Okay. So in our microcontroller data sheet, I am going to open our microcontroller data sheet here. So if you go to electrical characteristics, need to know output low voltage, output high voltage. So there is a parameter which I am checking in order to consider a particular volt as high, that you can see somewhere in electrical characteristics only. DC and AC characteristics graph and table. Okay, let's say it's a 3 volt. So I need to get a 3 volt to read it as a high. I need to get a less than 1 volt or 1.5 volt to read it as 0. So right now I will replace this temperature sensor. In future, maybe in next class, I will connect this temperature sensor to port A. Wait, we'll connect it now only. Port A. So port A reading method is different. It is analog reading. So right now we are going to implement or create the software with the digital reading. So this was my plan, so that you will learn all this control structures and software development process in a quicker way, and you will get a good picture of that. So right now I am deleting this from here. So let's see, I am in that place. I will keep one button. So this button will act as a temperature sensor. If the button is closed, temperature is high. If the button is open, temperature is low. This way we will implement a software at first. Later we will implement with the temperature sensor. Just observe how I am drawing the software. If you can always try and learn. 10K is needed. Okay. So what I told, if the switch is pressed, temperature would be high, released temperature would be low. This is our first phase plan. Second phase we will implement with the temperature sensor. Okay, so we will go back to code. I'll open one new session. MPLab XID. File, new project. It's a bit slow in response. File, new project. Microchip embedded application project. Next, you need to choose microcontroller PIC16F877A. No simulator model. Simulator. XC8 compiler. I am going to save the project inside a particular folder which I already created. It is automatic temperature controller. Inside that subfolder is there, software. I am going to save my software over there. Project name, automatic temperature controller. Finish. Now you can see our previous LED blinking project here and the current automatic temperature controller project over here. But initially, to avoid confusion, I am removing the old project. So where is the delete button? Close is there. Yeah, okay. I'm closing this start page. Now go to source file or right click over the source file. Why it is not coming? Got stuck. Okay. You can hear me, right? Hello.
Yes.
Okay. Yeah. Thank you, Vaishak. Source files new main.c. Okay. So here I am going to give main. So this process we always have to repeat once we are doing and while we are doing a new project. So yeah, we have a template here. Now we will start writing our software. So today I am going to tell one new thing which is called macro. It is a preprocessor directive in C. Macro. Okay. So macro means there are many other things in macro, but I am telling the one among them. Okay, which is like this: hash define. We have buzzer in our software, right? Or we have an LED in our software. We have a red LED here. So I am going to write like hash define red underscore LED, red LED, which is the pin number RB0. So it will make our software more readable. easy to debug. Okay, so that's why. So what happens is, uh, we are creating a constant. We are creating a constant, a memory location called red led, and it is pointing to an address which is given by RB0. RB0 is already known to the compiler. RB0 is a particular pin of our microcontroller. Once we tell our compiler that the constant which we created, constant is a memory location, the constant which is created is representing RB0 pin. Okay, then next we will write hash define buzzer, which is in RC0. Okay, RC0. Next we will write hash define temperature sensor, which is on pin RD0. Next we will write, we have one thing over here, that is fan, hash define fan. On, fan is on RD7, which is controlled with the help of a transistor, power transistor TIP122. I will explain the working of this circuit later, or else you can take a screenshot right now and you can self learn how it is going to work, how this particular fan would turn on. Maybe you people already know, some of you, or else I will explain once that part of software code we are writing, that part of software code. Okay, so it is RD7. So RD7 is fan. Um, Here we are not able to, we are not thinking about this right now. In next class or in upcoming classes, we will think about temperature sensor. Okay, so this is called macro. Uh, Hash define, with the help of hash define preprocessor directive, we defined few macros for LED, buzzer, temperature sensor, and fan. Now we have to tell the state of that particular LED. Like how can we turn on that LED and buzzer? Okay. So for all those, for both LED and buzzer, turning on is done by. I mean, turning on is done by making this particular pin 0, right? Okay, so here if you write 0, LED will turn on. Here if you write 0, buzzer will make sound. Okay, so what I am going to write is hash define, I am writing capital always, hash define on 0, hash define of 1. So this is how we came into conclusion. So off means 1, on means 0. You will understand when the software implementation is progressing, so you will get a good picture in few minutes. Okay. So on is 0, off is 1. Now what is remaining? Temperature sensor. Temperature sensor, we have two states, high or low. Temperature high or temperature low. We are going to define the states with the help of this macro hash define high means 1. Sorry, temperature high means, okay, yeah, 1. Hash define low means 0. Now what is remaining? Fan is there, right? Fan. Okay. For the fan, how is the status? Okay. I am going to tell the working of this circuit. Okay. Without that, we can't write the status. Okay. So this is a relay. So the customer told they have a 230 volt a fan which is working on 230 volt. So this fan, imagine that this fan is working in 230 volt. So how will we connect? Our fan would have two wires, maybe three wires. One is earth, leave it. Remaining two wires we have phase and neutral. Phase we are providing to one wire and neutral we are providing the to the other wire. Then if you turn on the fan will rotate, right? So right now the fan is rotating manually with the help of a switch. We need to automate it. So the customer need automation. So our microcontroller which is PIC16F877A or the system which we are making is working on a low voltage, working at low voltages, right? So it is working at 5 volt, and our microcontroller can generate 5 volt or 0 volt. So we can directly connect that 230 volt AC fan with the microcontroller. Okay, so what will happen, it won't be able to turn on the fan because the fan need 230 volt. Our microcontroller can only provide 5 volt. So, so it is impossible to directly drive this particular fan as we did with LED. LED we can drive directly, right? Because our microcontroller can drive that much voltage, sorry, that much current with that much voltage. But in the case of this fan, it is not like that. Fan is working at a higher voltage and current, and that is not, and our microcontroller is not capable of handling such high voltage and current. So we need a intermediate person, which is called relay. Okay. And there are few first year, second year people here. They don't know how the relay looks. Relay module. So not relay module, relay. Okay, for those people who don't know relay, these are the images of a relay. Okay, I will take this picture. You can see three pins over this side, two pins over this side. NC means normally closed, NO means normally open, and we have coil terminals over here. Okay, so relay is practically a switch, but it is electromechanical switch. If you are giving some voltages to the coil terminals, it will turn on. Turn on means there is a permanent connection between the common and normally close. Okay, you can see this diagram. You can see this diagram. I am taking this diagram. Okay, this is an SPDT relay, single pole double through. So double through means it has two output, normally open and normally closed. Single pole means only one connection, common COM, only one COM. Okay. There are many different types of relays. If you are interested, you can always browse Google and learn. Okay, so normally open means this common connection would be always connected to normally uh, or normally close pin. I mean common connection is normally connected to close pin. You can see in our circuit diagram also. So here you can see common connection is there, which is always there in connected to um, one pin which is normally closed. Once this relay is activated, the relay will be activated once we give some energy to that particular coil. So you have coil pins here, right? Where is that other image? Okay, no problem. Okay, this pin. So you have coil pins here, right? When you provide some energy to the coils, it will energize and it will get magnetized. This picture it will get magnetized and will attract this particular pin here. You can see that when once we write the software and it once it is working, you can see that movement. So once the relay is on, how it will turn on? Once, with the help of our microcontroller, we are telling this transistor to turn on this relay. Okay, why there is a transistor here? That is another question, because we can't drive the relay directly with the help of microcontroller, because microcontroller can't provide 12 volt. This relay is working on 12 volt. Then you will ask, 5 volt relay will be available in market, right? Yeah, 5 volt relay is available in market, but it won't be able to drive provide sufficient current. That's why we are using drivers. These are hardware drivers which helps them relay to which helps the relay to drive properly, which helps the microcontroller to drive the relay properly. So here this TIP22 have sufficient TIP22 transistor have the capability to drive this 12 volt relay properly. So it can handle sufficient collector current. So what will happen once we want to turn on the relay, we are telling the transistor by writing a 1 here. So RD7 will become 1. The transistor will start conducting. So the transistor is configured as a switch. So it will come into active region, sorry, saturation region. So once it is saturated, you have a 12 volt connected here. That 12 volt will produce a current through this coil, and that current would travel through collector, through base to emitter. So there would be a current flow through the coil once the base is high. So that current will energize the uh, magnetic field, create a magnetic field, and that magnetic field will attract this switch. Then the circuit will be open. Open means this fan would not be rotating. So if you want to rotate the fan, the relay should be off, or else you can write it in a circuit you can create in a this way. If you want to turn on the fan, relay should be on. So this switch comes here, right? Then 230 volt would be, so I will make it is AC. Okay, not needed now. Think that this is an AC fan. We don't have AC fan in Proteus, that's why. Okay, so 230 volt would come over here and it will go through this switch, and this DC AC motor will start rotating once the relay is energized. So what is our need here? So here RD7 should be high. Okay, so turn on the fan, we need a high. So on is already there, you can't use that on. So what we are going to use, a new word is needed, as define. You can write enable, or you can write underscore on. Okay, enable means high. So enable means you are enabling this coil. Okay, so enabling means you should write a high over here. Enable means high. Hash define and disable low. Okay, so everything is ready. We will come back to this discussion if you still have doubt, but that doubt will vanish once we write our software code. Okay, so right now I am going to initialize our port pins. TRISB. TRISB. We have one device which is LED. So I know what I have to write. TRISB equal to 0x00 will make all the port B pins output. And I have one more pin RC0, which is this one RC0, that is buzzer. Remaining all are unused. So I am blindly writing TRISC, TRIS. C equal to 0x00. Uh, are you able to see the code which I am writing? Is this visible in your screen?
Yes,
Okay. You can read the code, right? What I am writing over there. Tris C, Tris B. I am trying to uh, increase the font size. Is that needed or is that readable? You can read the code, right? That's what I am asking.
yes, it's readable.
Okay, okay, thank you. Okay. So, yeah, Tris C, the status is uh, the initialization code is 00. You know, Tris C, we have only one output. We should write 0 in the Tris register. Also, Tris C, we have, sorry, Tris C already wrote, and port D. Port D, we have one input and one output. So, where is that input? Input is at RD7 and output is at RD0. So, the initialization will be like this: TRISC equal to equal to. If you are still confused in writing that initialization code, use calculator. Okay, calculator. Choose programmer option, select binary, and think seventh bit. What is seventh bit? Seventh bit is input. So in calculator we are providing 1. Sixth bit is not using 0. Fifth bit is not using 0. Fourth bit is not using 0. Third bit is not using 0. Second bit is not using 0. First bit is not using 0. Zeroth bit is output, so it is 0. So this is the value, and you can see the hexadecimal value here 80. You can write it over here 0x80. Okay, so these are the initialization for the direction control of the pins. Now we have to write the initialization for the port pins. For that, port b equal to, I'm copying this entire thing. Just need to, so all the port, there are port registers, right? Port. So port B, how should be the implementation? It should be 1 in order to turn off this LED. If you want to turn on LED at startup, you have to write 0 over here. So I am writing 1 over here in order to make that particular LED off at the time of initialization. When the microcontroller boots up, it should off. So that's why I am writing 1 over there. It's all based on the working of our hardware. Okay, so try to understand, try to have a picture of these things in your brain, then you can play with it. Next, port C, what is the status? We don't need the buzzer to be on at the time of initialization, so we have to write 1 here to maintain the voltage difference 5. So here also 5, here also 5 we need to turn off. So make it that pin 1. And tris C, this is input. You should maintain a voltage over here. So this should be 1 and this should be off. So this pin should be 0 and this pin should be 1. So 0 0 0 0 1. I'm making it 0 1. Okay, so this, by this our initialization complete. Now we are going to write a loop over here. What is the time now? Okay, we have 4 minutes. While is a loop, and we are writing a constant inside the expression. While one is an infinite loop. Okay, you can also write for without condition. This is also an infinite loop. Okay, so both you can use, while with a constant, for with a for with without statements, and without statements but semicolons. That makes an uh, that makes a infinite loop. Okay, so right now the structure is ready. Now we need to know what we have to do. We need to read the temperature. Okay, so for reading the temperature, so the customer would tell something like that. First, we need to have a beep at the power of, when you turn on this device, there should be a beep. The customer is telling like that. So we need a beep, B E E P. So we are writing beep. So what is beep? Compiler is telling she don't know what is beep. So we have to tell what is beep. So I am going to tell our compiler what is beep. So what is beep? Beep is actually turn on and turn off of buzzer. Okay. So what I am going to do is, inside beep I am going to tell buzzer equal to on. Okay. Then beep sound. What is beep sound? Ting ting. Buzzer should on and buzzer should off. So in between I need a delay. Okay. Then I should tell buzzer off. Buzzer off. This will make a beep sound. Ting off. Okay. Then the compiler is telling she don't know what is delay. Then I am telling what is delay. Void delay. Here I need a controllable delay. So I am trying to create a function uh, with an argument called int time. Okay, so we learned the function last class, right? So here we called a function called beep. So here you can see it is capital beep. Here I write a small beep. It makes confusion with the compiler, for the compiler. So that's why it's in red color. So beep is here, beep is here. So this is a function beep. It has a code inside here, buzzer equal to 1 after a certain delay 10,000. Okay, also we need a delay after turning off. Okay, okay, compiler is not aware of what is delay. That's the problem. Now we have the delay function also. Now everything is clear. Now compiler is aware of what is beep, what is delay, but inside delay there is nothing. Okay, so I am going to implement that delay also. Inside that delay I am going to write a nested for loop. What is nested for loop? We discussed in last class. Nested for loop is a for loop inside a for loop. For int x equal to 0, x less than time, x plus plus. Inside that for loop we are going to write one more for loop, which will give us a huge delay, y less than some 100 we will provide initially. Next class we will try to use the debug feature of our MPLAB XID, and we will find out how much time it is taking to execute one delay. Okay, then you will understand how the delay, for loop, everything is working. Okay. Right now you might have understood the modular approach of program development. So here we need a beep. Here we need a beep function. So to make the program modular, we made a function called beep here. Inside that beep, we are using a delay. For that, we created a delay function over here. So so this function, the way of creating program with the help of function, makes our program code more compatible and readable and maintainable and debuggable. Okay, so these are the feature of using a function in your code. So beep sound will call this function, buzzer will get on, after a certain delay buzzer will get off, when a certain delay it will come back and tell what to do. Then the customer is telling they need to turn on the LED. Okay, they are telling they need to check a switch, which I already told, right, which I already mentioned here. There is on auto manual switch and an on off switch there, which is not drawn here. So let's imagine that switch is at RB1. RB1 we have one automatic switch, and RB2 we have one RB1 we have an auto manual switch, and RB2 we have this particular on off switch. Okay, we will write that we will update the circuit diagram based on the requirement, and we will add those auto manual switch over here. Also we will add that on off switch also here. Then we will go to write the next code below, that is like if AUTO auto underscore switch equal to close, we will tell the controller to do something. So we will plan our software wisely, and we will come back next week. Okay, so till now if you have some doubt you can ask, you can clarify right now, or in future after the class, if you have some doubt you can always put a voice note over the over my WhatsApp number. I can provide a reply. Anyone wants to ask something? Febin, is that clear for you? Hello, Febin.
Yes, sir, clear, sir.
Okay. So yeah, remaining software code and implementation we will look in our upcoming section. Okay, so we will meet next week. Yeah. See you then. Bye bye.
Bye.
Bye. Bye. Yeah.